Okay, so good morning, everybody. So we're going to have to switch over to that different visual for when we play some speech files. So anyway, Richard Jobson of Teraquant, and we're based in Boulder, Colorado, and 17 years in business. So we're coming from test and measurement. So I'm not really a computer scientist, as you've heard about previously in the other speakers. I'm more of a telecom person, I guess. And we're all about testing speech quality and then using what we learn from speech quality to troubleshoot real problems on voice over IP networks. So we work a lot with service providers and their operations departments, and also increasingly enterprises or corporations troubleshooting problems, but we also, in operations, but we also work with the vendors. For example, people who measure the codecs or produce the codecs for these things, and wherever voice codecs go. So let's see what we're going to discuss today. So talking about the operational environment, we're going to look at what problems we encounter typically from different parts of an operational voice over IP network, and what problems they might represent. So then we're going to have a quick look at this technology. You've all heard of MOS scoring, right? Well, MOS, good, some nods. Bit of tautology there. MOS stands for mean opinion score. So it's the mean opinion of lots of people judging different clips. We'll look at that more closely. And it stands for mean opinion score. So when you say MOS scoring, it's mean opinion score scoring. Anyway, so we'll have a look at that. And so there's different technologies that produce a MOS score. And we'll have a look at what each of those technologies, different types, like you've maybe heard of PESC. What's the difference between PESC and what you get from your monitoring tools? And how does that help you troubleshoot real problems on the network? So that's what we're hoping to achieve this morning. So we'll have a look at those different audio perceptual metrics. And then we'll have a look at some of the impairments or defects or problems that we can encounter on the network, where they come from. Do they come from the network? Do they come from the endpoints? And how can these MOS measurements help us troubleshoot the root cause? And then we'll just have a look at how these MOS techniques, the objective MOS techniques, are deployed on the network. So that's what we hope to achieve today. We're starting a bit late. Somebody keep me on time so we don't go over. We've got time for some questions. So yeah, a bit small print here, but in the telecom network, whether it's enterprise or service provider, we have complex situations. We have transcoding and compression going on. We might have voice activation detection. So in order to save the bandwidth on the network, if we don't speak, we don't send packets. So what threshold do we need to speak before we start sending IP packets again? So that's all tied up with voice activation detection. And then we have sophisticated packet loss concealment techniques as well. So if we do drop packets, maybe we try to regenerate them at the other end so that we can have intelligible speech. So these are all mechanisms going on within the network that we might find issues with. We need to test and monitor. Do we have quality of service set? Do we have prioritization set? And so that the voice packets are highest priority because they're real time, cannot be dropped, should not be dropped. We have broadband networks, we have a lot of SD-WAN creeping into the network now, more complexity, not everything is nailed up with a pure fiber connection from A to B or even over an MPLS network. So this, as we reduce costs, obviously, we may have a compromise on performance. Then we have the interface between the legacy networks. We still have some analog pieces within a network, right? Especially with international phone calls. You never know where it might go. Again, it's not just fiber, it's maybe not just even an IP connection end to end. And so what impact does the network have on the quality of the call? Transcoding, right? So we might go from G711, which is typical narrowband PSTN type voice over IP. We might transcode that into a wireless network. So this thing here does not use G711, right? It uses a different codec. So what happens to the quality when we go over there? And then, of course, the packet level impairments. We mentioned packet loss and jitter and compression of the voice. We might have voice path might go over a satellite network. Obviously, introducing latency issues, mentioned VAD. We might have echo or noise. Echo, incidentally, is not included in our friend, the MOS measurement. So MOS measures speech clarity. It doesn't measure latency and it doesn't measure echo, so we have to measure those separately. So this is an idea of the situations we might find on networks, and how are we going to troubleshoot them? So I'd just like to give a little example here of the typical speech defects we get, and we'll first hear packet loss in the first sentence. This is the first sentence here. We're looking at the degraded instance. And at the end, we'll hear something which is definitely not packet loss, jitter, or IP network related at all. So let's see. I'll just have to hop over here and oh dear. Excuse me. Correct. Select the right one. Right. So.
Le tribunal doit bientôt rendre son jugement. Mes yeux s'accoutument lentement à la pénombre.
Got everybody's attention, right? So, I can play that again, but in the first sentence we heard packet loss. And in the second sentence, what we heard was total loss of synchronization of the codec. And so it was skipping frames and missing frames and playing out a mixture of frames. And that's why we got the loud squawk at the end. Should I play that again?
Le tribunal doit bientôt rendre son jugement. Mes yeux s'accoutument lentement à la pénombre.
So here we can see the packet loss. So here we're seeing the errored surface. This is what we play into the network. This is what we get out, what we call the degraded file. Here you can see discrete losses of energy. And here, actually, you see energy introduced erroneously into the system. So this is using a technique known as polka. So polka, so we'll come back to polka in a minute. But if we just back up and talk a little bit about MOS. MOS scoring. So MOS is actually a subjective measurement. It is, what is MOS? Well, literally, it is lots of people in a room or in a lab or crowdsourced listening to tapes, clips, audio clips of varying different levels of quality and scoring them on a scale from 1 to 5. Not from 0 to 5, from 1 to 5. It's an ITU standard in terms of ITU P800. Tells you how to do the experiments, how to get in the lab, and what kind of environment and to produce these clips, to get repeatable estimates from the people who are scoring them. So that's MOS. And so obviously in a network and also in the lab, we want to, sorry about that. Bound to happen, isn't it? Okay, so we now want to get a computer to produce these MOS measurements. So we've got different computing techniques or algorithms to do this. Many are, if not all, are standardized. And so I just want to create an awareness of the different types there are. Basically, everyone's used a sniffer, right? Everyone's used Wireshark, right? You monitor on an IP network and you measure packets, and it might even detect when there's a missed packet. And it might even give you a MOS score. Well, if it's giving you a MOS score, it's based on a thing called eModel, and basically it's measuring packet loss and jitter. So if we have other things related to the endpoint or transcoding or those digital signal processing things that are going on at the audio layer, it's not really taking those into account. So, however, eModel is the only thing that really scales up to like 10,000 concurrent RTP sessions, right? So if you have an operational network with thousands of sessions, then you have to use eModel. It's a light touch, you've got a certain amount of CPU to apply to this problem. And so that's eModel, but it's basically going to tell you you've got packet loss or jitter. In a lab, or if we want to test things at the audio level, then we would use PESC, which was one of the earliest standards, came out in 2003. And then Polka, so there was some improvements made on the PESC algorithm to come up with Polka. Polka also went to wideband telephony, so G722 codecs. Here we see, spectral graph, narrowband telephony, wideband, super wideband, and full band going to the 24 kilohertz. So things like Opus and latest codecs now, EVS from Qualcomm, which will be the new codec that goes in the handsets, goes to full band. And so we're using Polka testing at the audio lab. You bet, absolutely. Yeah.
Isn't it strange that we end up with 5 maximum? I mean, you come very close to 5, even on an old telephone network starting from 300 hertz to 3.5 kilohertz, with a MOS score about, 4.8 or 4. Very close to 5.
4.3. Right, for a local
and then
loop.
If you add this feature and get hi-fi quality and everything, you still don't get beyond
Great
5.
question.
It's a very strange scale, isn't it?
It is a very strange scale, and it may need to get modified.
Comment on that, and are we going to do something better? I hope it was 10 or when I've done all my improvements.
That's a great question. So the answer to your question is, hopefully, this is my answer anyway. I'm sorry, it's the answer, actually. So although the scale theoretically goes to 5, the maximum that, on a statistically significant scale, the maximum we all gave, the very best narrowband PESC score was actually 4.5. Okay, so that, maybe one individual gave it a 4.99, maybe, but statistically the maximum we all get, there's about 850,000 last time I looked, of these measurement points in the global database. And the maximum they've ever given for a narrowband measurement is 4.5. So they use that kind of knowledge when they move to wideband, and they actually go to 4.75. So on wideband measurements, the maximum that anyone actually, or we all gave, was 4.75. It still wasn't 5, but it was 4.75. And so that is what the Polka algorithm wideband is tuned to, And that's the best you'll ever get on a Polka scale is 4.75. Does that make sense?
I have fine Wi-Fi stereo surround at home, and I put in a telephone in the middle of that.
Yeah.
I would be very sad and give it a 2.
Right.
So considering that, I think it's a strange scale we ended up with.
Yeah. I mean, there's some work going on in the standards committee.
You don't get much benefit for all the work you put in to improve it.
Yeah, because you spend all that much money. Yeah, and all you get is an extra 0.25.
Yeah. Okay.
Right.
Thank you.
It's a good point. I mean, so when we're doing video quality, right? When somebody looks at a screen this big, they go, "Hey, that's pretty good. I'll give it a 4.4." Right, but when you've paid for your 60-inch, $5,000 or whatever it costs, 4K, and you got that, I'm only going to give that a 3. Well, actually, it's the same quality. It's the actual same pixels on here as it was on there, but you expect more from that. So psychology comes into it. But that's the scale at the moment. And if you get a 4.6 and a 4.7, that's consider you've invested your money well, because you're doing better than what you got for narrowband. Okay, so thanks for that question, and it's good. So just what we're doing here, in contrast to the sniffer and the Wireshark, where we're passively monitoring in a number of different places, with an audio level measurement, we're actually generating some audio out of these analog interfaces, putting them into your analog interface, which might be take off the coily lead off your telephone and stick it in there. It might be this interface right here I have plugged into my computer so I can test the software. It's analog. And I'm putting an analog sound into that system network, receiving it back, and comparing the two. So that's the two are the reference file and the degraded file, and then we get a result. So this is how we can measure beyond the IP network and measure endpoints as well. How are we doing for time? Okay. 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 How much more time do I have? 7 minutes. Okay, we can do it. Great. Okay, so back up to the typical operations network, and the E-model methods for calculating a MOS score. And what does that do for troubleshooting? Well, you would typically monitor at different parts in your network. Got a light pen here, and so we would probe with probes, passively monitoring at the access link, if you like. Maybe Alice is a remote worker. We want to monitor as she hits the PBX, the typical corporate network. Certainly between the PBX and the SBC, session border controller going out to the SIP trunk and off to Bob on the PSTN. So here's where the corporation enterprise network might lose control of it, so you definitely need to monitor that. So basically, if you have no packet loss here, no packet loss here, but this is where packet loss creeps in, then you can isolate as to where the problem has crept in. And so you might want to look at a display like this, so you can pick out on the right, you can see that the average speech quality, here we've got a MOS, an E-model MOS of 3.94. That's pretty good. Intelligible. Certain times the minimum MOS in the call has dipped down to 1.39, and then in the middle we can say which physical segment it was, and here we have a time axis, and we can see that the problem was intermittent. We got packet loss here, and then it went away. And so we can isolate where in the call, or where in the voice path across the network it happened. We might also be able to detect one-way audio as well, which is a common voice over IP problem, as I'm sure you're aware. So have we time for another speech clip? Thanks. So just to show you again packet loss and what it sounds like.
These days, a chicken leg is a rare dish. The hog was fed chopped corn and garbage.
Okay, so I happen to have picked two phenomena that are fairly close together in terms of what they sound like. So, you know, we have this picket fence, they call it, to describe the sound of packet loss. Picket fence for packet loss. I mean, that's how you can remember it. So this is the problem that's going to be solved by just passively monitoring, and we can pick out packet loss and jitter and isolate it where it is within the network. If we have problems relating that go beyond that, we have a clean network, we see we've got zero packet loss, customers still complaining of problems, we need to dig deeper, we need to do measurements at the audio layer. And so we need to generate audio files into the analog interfaces right at the edge of the network. So just to summarize, root causes of speech quality problems on operational networks. You could categorize them in relation to, yeah, great question.
Really quickly, if the only parameter you're exercising is packet loss, because that's the only thing that you're capturing, why not just report packet loss rather than this abstracted MOS?
Great comment. Hate to tell you, it's not the first time it's been said, right? So you are characterizing packet loss and jitter within that MOS measurement. It's just that everybody's latched on to the MOS score. And that's what they expect to see. And so it's just a leading indicator that's, yeah. I mean, obviously a lot of tools. We launched the Palladian system, which is now an Oracle product 10 years ago. This is what we're looking at here. We can see the red bits, bad MOS. This screenshot down here is produced by Palladian. Obviously, it will tell you jitter and packet loss and MOS. It'll also tell you whether you're being reported from the actual RTP packets and or the RTCP. And so it's like and often those measurements don't agree because of averaging intervals and because of implementations, and you need to understand where the RTCP measurement is coming from, which device is producing it, and where in this scheme of things am I monitoring my RTP, okay? And so is the RTCP coming from the SBC? Is it coming from the SIP trunking vendor, which it may do? And it should be coming from the endpoints. So these are some of the issues that it's useful to be mindful of. So I played the one showing packet loss, which is kind of more sharp cutoff of the voice indicating packet loss. So I'll just play you a clip here we have showing something else that may happen. Obviously, when you put clients on PCs, you starve the PC, and there are compromises being had by running a telephone on a piece of software, hate to say. And so here's an example of where the audio is being starved for resources on the endpoint or on the PC, if you like, using a soft phone.
These chickens are red dish. Hogs were fed chopped corn, garbage.
Okay, just one more time.
These chickens are red dish. Hogs were fed chopped corn, garbage.
So where the audio is cutting out is just less digital than in the case of packet loss. Okay, so I just wanted to give you an appreciation of how these techniques can be used for troubleshooting. Okay? Oh, we got a... Have we got time for the question?
Do you need to end it?
We're in keynote in 10 minutes, so if we could do the question offline, that would be helpful.
Okay. Thank you.